Now we're on to question 58 on assignment 18. And in this case here, you're asked about finding the equilibrium constant in a pair of reactants that are mixed together. So for part A, those reactants are silver and manganese 2+. And you want to find K, which you will get from E0 cell. So you need to figure out the two half reactions in this case. So you have to think about what's actually happening. You know the reactants, but you don't know the products. So if we were to start with silver, you have to think about what silver can turn into. Oxidation state of silver is 0. So if it is reduced, that oxidation number is going to go down into the negatives. We know we do not have those for silver. So it's most likely going to be oxidized. And our most common one that we oxidize to is silver plus. So this is what's happening in this case here. And to balance that, we need an electron. So if this is our oxidation, that means that the manganese has to be a reduction, because we know a few different things can happen with manganese. It can either be oxidized or reduced. So we know it has to be a reduction in this case. So think about what it could potentially be reduced to. If I'm at 2+, I'm not going to go into the negatives. There's no manganese plus under regular aqueous conditions, but I do have just regular metallic manganese, which is solid manganese in the 0 oxidation state. To balance, 2 electrons, and that one's good to go. To balance these together and add the 2 together, I would have to multiply this one by 2. And we can go ahead, cancel our electrons, and add everything up. Now you need to find E0 of the cell, which means you need to find the E0s for each of these half reactions. Remember, they're always written in the reduction direction. So you're going to find silver plus going to silver. And in that case there, it's plus 0.8. But the way we've written it here, it's going to be a minus 0.8 volts. And we can go and find the reaction of manganese 2+ to manganese. And that one is minus 1.18 volts. So our total, E0 cell, if you add all these together, is going to be minus 1.98 volts. And just like the question before this one, 42, our equation for K comes from this one here. So we just found E0 cell. Z is the number of electrons transferred in the balanced equation. So in this case here, Z is 2. F is Faraday's constant. R is our gas constant, 8.314. And 298 for our temperature. So after you do that, solve for K, your answer should be 1 times 10 to the minus 67. Now I'll just set up B, and you can do the rest of that yourselves. I'll balance B. We won't do the actual numerical part to it. So in B, you're given Cl2 and Br minus. So those are your two reactants. You have to figure out what's going on. So just look at the oxidation states in these cases. Cl2 is 0. We know we can have negative oxidation states for Cl, and we can have positive ones. So we're not sure what's going to happen in that case there. Br, this is now minus 1. So we can't go any lower than this for Br. This is a halogen. That's as low as it's going to get. So we can only go up, which means that this will be oxidized. And we've seen these equations many, many times where we have Br minus, and it goes up to the 0 oxidation state, Br2. So to balance this, 2 Br minuses and 2 electrons. So that's our oxidation. This is telling us now that the Cl2 is going to be reduced. So if that's a 0 oxidation state, and I have to go down in oxidation states, I have to reduce it. The only other one I can go down to is minus 1. Again, this is a halogen. That's as low as it's going to get. So that will be chloride. Balance this as such. go through then. This one's nice and easy. You can see how you get to your final equation. So in these reactions or in these types of questions, it's a matter of figuring out which one can go where, and pretty much you're always going to be left with one that has to either go up or down. And that's going to be your starting point, either oxidation reduction, and the other one is going to be the one after that. And you can continue the rest of this question just like we did in part A.